Good morning. Today we are going to walk through some common stumbling blocks for roughly the second half of Unit 2 for the AP Physics 1 curriculum. Specifically, universal gravitation, spring force, and circular motion.
Flippin' physics.
First, there are two equations for the force of gravity. You need to know what they are and when to use them. Bobby, tell me what the two equations are, and Bo, tell me how to use them.
One equation for the force of gravity is Newton's law of universal gravitation. That states that the force of gravity equals the gravitational constant
Big G
times the mass of one object times the mass of the second object, all divided by the square of r, the distance between the centers of mass of the two objects. The second equation for the force of gravity is that it equals the mass of the object times gravitational field strength.
Okay. Newton's law of universal gravitation is always true.
Really? But we typically use that equation for planets and stars, right?
Sure. However, because the equation is universally true, we could actually use it for an object on the surface of a planet, or even two smaller objects which are infinitely far from any other objects in the universe.
How often does that happen?
A lot in physics multiple choice questions, evidently.
Valid.
The other equation,
Force of gravity equals the mass of the object times gravitational field strength, is true when the gravitational field is constant. In the thin plane of existence where humans live on the surface of the Earth, the gravitational field strength is considered to be constant with negligible error. In fact, on the AP exams, we simply use 10 newtons per kilogram instead of 9.81 newtons per kilogram. I thought the units were meters per second squared.
Newtons per kilogram and meters per second squared are equivalent. It is just that we typically use newtons per kilogram as the units for gravitational field strength and meters per second squared for the acceleration due to gravity, but really they are the same thing.
Okay.
sure.
Also, you can set the two equations equal to one another to solve for the acceleration due to gravity near the surface of any planet. The force of gravity equals big G times the mass of the object times the mass of the planet, all divided by the square of the distance between their centers of mass. And the force of gravity also equals the mass of the object times gravitational field strength. And
Everybody brought the mass of the object to the party.
Everybody brought mass.
And we get that the gravitational field strength caused by a planet equals big G times the mass of the planet, all divided by r squared. But remember, r is the distance between the centers of mass of the two objects, so for an object near the surface of a planet or orbiting a planet, r equals the radius of the planet plus the altitude of the object, and altitude is the height of the object above sea level.
Nice.
Yeah.
Thanks.
Well done, everybody. Bo, what is the equation for the force of static friction?
The force of static friction equals the coefficient of static friction times force normal. What?
That is not quite right.
Oh, yeah. The force of static friction is
Less than or equal to the coefficient of static friction times force normal. Is that really all that different?
It absolutely is. Do you not remember the Friction AP Physics 1 Unit 2 review supplement lesson that we were in where Mr. P specifically went over the importance of that less than or equal to sign?
Or the many multiple choice questions in Mr. P's AP Physics 1 Ultimate Review Packet and Ultimate Exam Slayer, which give lots of examples where we have to remember that less than or equal to sign?
right.
Right.
Yeah, I'm not going to take the time to go over that right now because I do have lots of other resources which go over that. But yeah, you really do need to understand the importance of that less than or equal to sign. All right, next is a source of contention for some of my students. Class, does the force of friction depend on the surface area of the two interacting surfaces?
No.
I just cannot say it.
Yeah.
I know.
It's not easy.
I know. Give me a minute. Realize that, according to the standard model for friction for physics, the surface area between the two surfaces does not affect the coefficient of friction, so the force of friction is independent of surface area.
But
Right. Just hold on. We have our two equations for the force of friction. The force of static friction is less than or equal to the coefficient of static friction times force normal, and the force of kinetic friction equals the coefficient of kinetic friction times force normal. Class, is there anything about surface area in either of those two equations?
No.
And that is the standard model for friction for physics. And that is what is used in all of the AP physics courses. Now, when at least one of the surfaces is deformable, then the force of friction does depend on surface area. However, again, we do not consider cases where either surface is deformable in any AP physics curricula.
But car tires.
I know, car tires are deformable, and therefore surface area does affect the force of friction for car tires.
But Formula One.
Yeah, I know. A lot of things are simplified for AP Physics 1. No air resistance, point masses, massless strings, massless springs, frictionless surfaces, frictionless and massless pulleys, zero loss of energy during any event, uniformly accelerated motion, the gravitational field is constant, contact forces exist, circular orbits, rigid bodies, symmetrical shapes, elastic collisions, incompressible fluids.
I get it. Thanks.
Thanks. For some reason, many students get stuck on the fact that friction forces do not depend on surface area.
Nice.
What? Stuck? Friction.
Oh,
That's funny.
funny.
Thanks. Now, I have already talked about the direction of the force of friction a lot, and I am not going to talk about that today. However, I will point out that I have an entire lesson dedicated to helping you understand how the force of friction always opposes sliding motion. You should probably check that out. Next, I have some students who get confused about Hooke's law and the term natural length of a spring. So, let's start with Hooke's law. Billy, what is Hooke's law?
Hooke's law states that the force of a spring equals the negative of the spring constant times x, the displacement from equilibrium position.
Exactly. And Bo, what is the natural length of a spring?
The natural length of a spring is the length of the spring with no forces acting on the spring.
Yes. And Bobby,
A vertically hanging spring has a natural length of 5.4 centimeters.
if a mass is placed on the spring and lowered slowly until the mass is at rest, the new length of the spring is 10.3 centimeters. What is the displacement of the spring from equilibrium position?
Well, the equilibrium position of the spring is when the length of the spring is at its natural length, or 5.4 centimeters. Let's call that the initial length of the spring. And the new length of the spring is 10.3 centimeters. Let's call that the final length of the spring. And we are solving for x. The final length of the spring equals the initial length of the spring plus the displacement from equilibrium position. So x equals length final minus length initial, or 10.3 centimeters minus 5.4 centimeters, which is 4.9 centimeters. The displacement from equilibrium position is 4.9 centimeters. That was not so hard. What gives?
Yeah, honestly, I agree with you. It is just that for some reason, I have students who struggle with the concept of the natural length of the spring, and I feel like this demonstration makes it very clear what that is.
Sure, I think it does.
Another common stumbling block is the assumption students have that an object moving in a circle at a constant speed is not accelerating, which is incorrect. Billy, please explain.
Okay, explain why an object moving in a circle at a constant speed does have acceleration. Well, as you can see with the little green poker chip moving in a circle at a constant linear speed, let's add the arrow vector to illustrate the linear velocity of the green poker chip. Remember, velocity is a vector, so it has both magnitude and direction. The magnitude of the linear velocity of the poker chip is not changing. However, the direction of the linear velocity of the poker chip is changing. Therefore, the velocity of the poker chip is changing, and therefore the poker chip must have a linear acceleration.
Exactly. The key here is that while the poker chip does have a constant linear speed, the linear velocity of the poker chip is changing because the direction of the linear velocity of the poker chip is changing. So the poker chip has a linear acceleration. That linear acceleration is called centripetal acceleration, which equals tangential speed squared over radius. And centripetal acceleration is always directed inward toward the center of the circular path the object is moving through. Lastly, the centripetal force is the net force in the indirection on the object, which causes the centripetal acceleration of the object, which causes the change in direction of the velocity of the object. The net force in the indirection equals mass times centripetal acceleration. So the net force in the indirection equals mass times tangential speed squared over radius. And please realize the centripetal force is not a new force. The centripetal force is the net force in the indirection. So the centripetal force is never, ever a label used on a force in a free body diagram.
Actually, the green poker chip is a good example of that. The free body diagram for all the forces acting on the poker chip are the upward force normal, which is out of the screen, the downward force of gravity, which is into the screen, and the force of static friction, which points inward toward the center of the circle.
Bo, that is a valid point. You can see in this example that the net force in the indirection is the force of static friction. So in this example, the centripetal force acting on the green poker chip is the force of static friction. And that is an example of how it always works. The free body diagram never includes a force that is labeled centripetal force because it is not a new force. It is just the net force in the indirection. So whatever the net force is in the indirection, that is what the centripetal force is. That is the force that is causing the change in the direction of the linear velocity of the object and making the object move in a circle. Thank you very much for learning with me today. I enjoy learning with you.